benefit from this seminar, much more if you use that book.
Sure.
Well, there are thousands of books. It's a very old subject, and that book is much more modern. In particular, in the second volume, there are applications and some really exciting stuff. That I mean, this is just a classical PDE book that, I mean, if you go, I don't know, 60 years ago, it would look exactly the same. It is that subject. Whereas Taylor's book uses some exciting new stuff as well.
Right.
It just reads very differently, and also it has very nice set of problems, exercises, and some of them are real. I mean, I would advise you to do. I mean, in particular, even in this basic chapter 1, like things related to linear algebra, determinants, exponential matrices, and operators, and Duhamel principle, and a lot of things, very, very useful and used everywhere. Nice selection of exercises, that some of them you could do in class and illustrate that.
So I think maybe, I mean, if this sort of sounds like a good idea to everyone, if we continue with this book, and then if someone wants to present but they don't feel comfortable with it, they could pick something from anywhere else and sort of, you know, if at all possible, keep it logically continuous. But I'm interested in seeing everyone present. The only thing I'm worried about is that those who are not good with differential geometry, like myself, might get a little lost in the details when we are preparing for the presentation. But you're right, we can come to you.
You took 452, right?
Yes.
Why do you say that? What did you get?
It's just very difficult for me. I don't think as geometrically, I'm not as good with it. But that's personal. So I think that...
Well, you don't need to swallow the whole book. I mean, you get some ideas, he'll correct you, don't worry.
That's what I'm afraid of.
Yeah, given this is the first chapter right here.
Right.
It's a big book.
Well, it's up to you. I mean, I just...
Yeah, and I think that's a great
express my
idea to
opinion, but it's up to you.
I'm one of those geometry people, so.
Geometry. Right. So again, like if someone is has not taken 48 or has not taken 442, does not feel as familiar with maybe this material, I would say we should be open to them presenting something else. But I agree, this would be fine to continue sort of normally. I will set up a website, I think, and I will put maybe the next 2 or 3 as we sort of get into it. So I will give a preview of coming attractions deal and kind of overview what he's going to talk about. And then do we want to set up who's going to talk after him? So probably because it's new material, at least for me, I can't say at what point I will get to in preparation or in lecturing, so it'll probably kind of be, roughly speaking, which sections or which chapters. But does anyone want to volunteer to go after?
So why don't you say who is, well, today, are you going to cover any more material? Where does the
I will continue through what he will talk about, maybe in more detail.
But what? Could you say
Sure.
what exactly?
Yeah, it's so it starts with sort of getting at the idea of solution operators by. First I totally forgot, and I should have covered, but I'm not prepared to cover the inverse function theorem and the implicit function theorem. I can probably state those and talk about those now, and then we will only review them if need be. Then we talk about constant coefficient linear systems, and we define a matrix exponential, and we sort of talk about your research area in a very, very, very simplified form, which is the idea of solution operators, etc., if I'm speaking correctly. Then we'll go into variable coefficient systems of ODEs, discuss qualitative things like dependence of solutions on initial data, flow vector fields, Lie brackets, commuting flows, Hamiltonian systems, geodesics, variational problems, differential forms, and that's kind of the next 6 or 7 sections. So if anyone wants to take a look at this, the library has this book. Hopefully everyone got my email. They gave us a link to this book through Springer. Yeah,
so which sections are you finishing today?
I will hopefully finish just a very brief discussion of the inverse function theorem and the implicit
And
function.
the deal, which sections does he cover?
What do you think?
I haven't decided yet, but
Hopefully the
probably
next.
2 or 3 sections.
Yeah. So something like exponentiation of matrices, variable coefficient systems, systems of ODEs, which is Duhamel's principle.
Maybe just stop there.
Yeah.
Just 2 units and maybe something about the initial dependence on initial condition. I might just start.
Sure. And so probably where we would leave off in 2 weeks from now is flows, vector fields, Lie brackets, commuting flows, Hamiltonian systems. Those are the next 4 sections.
Well, if you want, if nobody volunteers, I could do that.
Okay.
If that's what you want.
And if someone volunteers
But
next
I don't want to turn this into another lecture
Mhm.
course, which would be boring. Okay, so for you, not for me, I mean,
Right.
it's just-
No, I think it's very useful for as many people as can and are willing to present.
Yeah, I'd like to present at some point, but I'd like to look over the book before I commit to something. So,
Yeah, so if you guys can look over the first chapter specifically, I hope we can get out of it in maybe 5 weeks. But that, that's sort of just my thinking. So yeah, let me see how poorly I can present this.
I kind of have appeal to Dr. Familia. I mean, everybody who's giving the presentation every time, he must have like some kind of weak areas or kinds of points that he doesn't really understand or need really elaboration or in-depth insight. That should be generalized to the participants of the seminar. So every time, I mean, if you are willing to just give a short conclusions and in-depth insights.
You
on
mean
topics.
before the seminar?
Or after everybody has.
Oh,
given-
at the seminar, okay, yeah.
That would be right.
So things I am skipping, by the way, are how we we take an nth order ODE and we can break it into a system of n first order ordinary differential equations. I think that's taught in 335 and several of the other courses, so I'm probably not going to go into that. We can also take a non-autonomous system that has time dependence and transform it into one without time dependence, which might lose some of the good properties of our original system. So the book suggests and sort of hints at that's not always a good idea. But I'm just sort of skipping over that. It's in the book. It's fairly straightforward. This is a little bit less straightforward.
Did you define what the autonomous system is?
No, I can discuss that briefly. So we have our system of ordinary differential equations, which we have written this way. If we say that f is only a function of the independent variable, then this is an autonomous ordinary differential equation.
I think this is called dependent variable. T is independent.
Yes. Dependent variable. Y is a function of t. And this has lots of qualitative properties in terms of we can shift things by t. We can change our initial time without at all modifying what the equation says. So in some sense, you can talk, once we get to vector flows, you can say that the flow is the same no matter what the initial time is. It has other qualitative properties, and this concept does generalize to partial differential equations in terms of both time and spatial dependence. Yeah. So this is section, I forget, section 3. As far as I'm aware, this particular theorem is not discussed in any class of tech that I've taken. So not in 471 or geometry or any other courses. So this may or may not be new to anyone.
Well, we do it in geometry, but there is, I don't
We do
prove
more
it,
generally,
but
yeah.
because we use that all the time.
Okay, so I'm going to also, and this is not in the book, so I'll have to remember this notation. I'm going to talk about the neighborhood of a point being the set X this the correct definition of a neighborhood?
Yeah.
Okay. So the neighborhood of a point can be seen as sort of points nearby, the distance that they have to be from each other. This can also be generalized to arbitrary metric spaces. This was what I was saying was the distance function. Distance within epsilon. And that will simplify this notation. Okay. So we have this map from a neighborhood